How do we measure y? What's the measurement of y? What units will we use? Feet. And what's our measurement of time? Seconds. So feet over seconds, that's our unit over here. Feet per second. I'm pulling the ladder out at 2 feet per second. At the moment the ladder is 8 feet from the wall, the point is coming down the wall, negative 0.873 feet per second. Why is it negative? Because it's going down, because y is shrinking. That's important, all right? If I was pushing the bottom of the ladder towards the wall, then the ladder would be coming up, right? And then this would be a positive number. What do you think? Some important things. When you set up your equation, you know how we replaced x with 8, right? That did not come until after you differentiated, right? We took the derivative and then you were allowed to plug in 8 for x. Never plug in your values for x or y. Never plug those values in for the moment in time until after you've differentiated. I'll try and give you an example of y, okay? And this is going to be ridiculous, but okay, I'm going to run across the room, all right? And when I clap my hands, that's when I want to know how fast I was going, all right? So if I'm running across the room and I go right there at that instant, I want to know how fast I was moving, right? I'm still in motion, right? And I'm telling you an instant time for you to tell me how fast I'm going, but I'm letting everything keep moving, right? That's what we're doing here. If you fix this to be 8 right now, nothing's in motion anymore, right? If this is 8, then that's what? 18.33, and everything's locked, and nothing's changing. Does that make sense? So that would be like me going like this. How fast am I going? So I'm not going, right? You stop me. So if you plug x in here, you're stopping the motion. I hope that makes sense to you. All right. There's the first related rate problem. Yeah, not too bad. Any questions? Yeah?
So that's how fast it's falling at that moment?
That's how fast, at that moment only though. A moment later, it's a different speed. But at that moment, that's how fast it's coming down the wall. Right here, at this point, right here, we could have solved for dy dt. We did that when I started class, right? And it came out to be like negative x dx dt over y, right? Yes? That was our general answer when I started class, before you even knew it was a word problem, right? I want you to look at this for a second, because this is actually pretty cool if you can see this relationship. If I take this picture, if the ladder's like this, okay? If the ladder's like that, so the bottom of the ladder is very close to the wall, right? And I start pulling it. We said in the beginning it's very slow, right? I want you to think about how big this is and how big this is. This is a very what? Small x, big y, right? If this is a small number and that's a big number, then this fraction should be small, shouldn't it? Small divided by big should be small. But if I do this picture, where it's almost at the ground, now the x is big, right? And the y is small. So if you take a big number and divide it by a small number, you get a big number. So you can see from this right here that the further the bottom of the ladder comes out, the bigger that the bigger that x gets, the faster it is. Do y'all see that relationship? It's kind of cool if you look at it that way. All right, we got to move on. We're already 40 minutes in here. We've only done one problem, so. The next problem is going to be a problem where what I'm doing is, imagine I have like a bucket of oil or something, okay? And I'm just going to start pouring it on the ground. And I'm going to pour it in a way that I start creating a circle on the ground, right? And the oil starts to spread out. And I'm going to pour it in a way that the radius of that circle grows at a constant rate. So I'm going to pour it very carefully so that I see the circle growing and the radius is always growing at the same rate. I'll show you a picture. Oops. Oh, what happened? Let me speed it up a little bit. It's a little too slow. Why does it not like that? It doesn't like that. All right. So we're looking from the top down, right? And what I want you to pay attention to hold on. I'm making sure this is the right animation. Yeah. I want you to just pay attention to me pulling this point. That doesn't look like the right one. Hold on. That looks like that radius is slowing down, isn't it? Hold on. I think I'm looking at the wrong one. Oh, here it is. Yeah, there we go. Now that radius is increasing at a constant rate. Do you all see it? If you were, imagine grabbing the end of this and pull it, that's growing at a constant rate. The radius is growing at a constant rate. The area is not. Okay, so I want you now to pay attention to the area. In the beginning, it's slow growth, right? Area is growing slowly. 6. Watch how fast this is going to go. 20, 30, 40, 50, 60, 70, 80, 90. See it speed up? So what's happening there is even though you're pulling the radius at a constant rate, the area is not growing at a constant rate. So what I'm going to ask you is at a specific moment in time, I want to know how fast that area is growing. Make sense? So I think I have this one. All right, so here's the problem. If the radius of a circle, I'm not going to write it down because it's in your notes. If the radius of a circle is increasing at a constant rate of 0.5 feet per second, then how fast is the area increasing when the radius is 4 feet? I'll give you a moment to kind of digest that. The radius of a circle is increasing at a constant rate of 1/2 foot a second. How fast is the area increasing when the radius is 4 feet? All right, let's get some pictures. Instant, general. Doesn't matter which one I draw first. I'm going to draw the general one first. I have a circle. It has a radius, right? And that radius is changing, right? And then my instant, I have a circle, but what's the radius? 4 feet, right? Some things to think about here. Do you know the area of this circle? Yeah. Pi r squared, right? That's the formula for the area of a circle, pi r squared, and you know the radius, right? So you could tell me what the area of this is right now, couldn't you? This, you couldn't tell me the area, but you could give it to me in a formula. You could say pi r squared, yeah? What are we given? We're given how fast what's changing? It says there, if the radius of a circle is increasing at a constant rate, right? So they're telling us how fast the radius is changing. And it's changing at how fast? dr/dt. We'll call it dr/dt. We're calling it dr/dt because we labeled the radius r, right? If we had labeled the radius h, I don't know why you do that, but you would call it dh/dt, right? How fast is it? 0.5, right? So 0.5 feet per second is how fast that's changing. What do we want? We want to know how fast the area is changing, right? So dA dt, right? Let's call it dA dt. Now our picture does not have a capital A in it, does it? Our picture does not have a capital A in it. But we know from this picture, right? From this picture, we know that capital A is pi r squared, right? We know that because we know what the area of a circle is. So we want this. At what moment do we want this? At what's 4 feet? The radius. So we want to say at r equals 4 feet. Whenever you write down what you want, you always want to put what it is you're trying to find, and you have to put the moment, something about the moment in time you're talking about. Okay, what's next? Equation. All right. What two variables are we trying to connect together? What two variables? R and A. We got to connect those together. Well, there we go. It's right there, right? So we have our equation. Area equals pi r squared. And now we need to do implicit differentiation, right? Implicit. Differentiating with respect to time again, to t, right? Of a equals the derivative with respect to time of pi r squared. Let's see how you handle this. Why am I differentiating with respect to time? Well, because the rate I'm given is with respect to time, and what I want is with respect to time. So I'm going to differentiate with respect to time. What's this? dA dt. Right? That's dA dt. That's a derivative of a with respect to t. So that's just dA dt. Am I happy to see that?
Yep.
Hell yeah, I'm happy to see that, right? Okay. How about over here? Careful.
2 pi dA dt.
Yeah, what about this pi? It's a constant, right? Constant attached to a function. So the derivative of that's not 0, right? It comes for the ride. So the pi comes times, now you can take the derivative of r squared, and you must use the chain rule. So what is the derivative of r squared? 2r times dr dt. So you bring the 2 out, make that a power of 1, and then you take the derivative of r with respect to time, which is dr dt. Am I happy to see that? Yes, right? I'm given that, right? So do I know dr dt? Yes, right? I have that. Do I know what r is? At the moment in time, I do, don't I? Yes, I'm happy. What's the only other thing here? dA dt, right? Am I happy to see that? Yeah, that's what I'm solving for. So I'm in business, right? I'm in business. I can plug everything in now. After the differentiation, you're allowed to plug in all the values. So, dA dt is equal to pi times 2 times 4 times dr dt was what, a half? 0.5? Can I put a half? Is that all right with you? Okay. So what's that? It's just 4 pi?
Yeah.
4 pi. So dA dt equals 4 pi. Now, if you wanted to get that as a decimal, you could, but it would be an approximation. You know, you could though, right? 4 pi. All I did there was that, right? 4 times pi. Now, you need to have the unit. Okay, so the easy part is time. We know how time is measured in this problem, right? Seconds. So I know it's something per second. But how do we measure area? We have feet here, right? So feet squared, square feet. So we're going to put here square feet per second. If I start pouring oil on the ground in a manner that the radius of that circle grows at a constant rate of half a foot per second, then the moment the radius is 4 feet, the area is growing at 4 pi square feet per second at that instant. An instant later, it's something else. Got it? What do y'all think so far? Okay. Okay, buckle up. I guess I could have left that there. You read the problem. All right. If the surface area of a sphere is growing at a constant rate of 20 square feet per second, how fast is the volume increasing when the volume is 36 pi cubic feet? Okay, so I didn't want to give you a picture of this yet. We all know what a sphere looks like, right? Okay. Surface area is the outside area of the sphere. The volume is how much material or how much stuff is inside of it, right? So somehow we need to connect the area of this sphere to its volume, right? So let's draw some pictures. At the instant in time, I have a sphere. So I usually draw a circle and then kind of like an ellipse or something through the center or through the middle like that. There's a sphere, okay? At the instant in time, do you know anything about this sphere?
20 feet squared per second.
That's the rate that something's changing, right?
The volume is 36.
Yeah, so it says there, how fast is the, maybe we should write that down. How fast, that's what we want, right? How fast is what increasing? The volume, right? So we want the change in volume with respect to time. I want dV dt. I'm using V for volume, that makes sense? I want that at what moment in time? At the moment that or when the volume is 36 pi cubic feet, right? So I want to know how fast the volume is changing at the moment the volume is 36 pi cubic feet. Do you see I'm doing this kind of like before I draw all my pictures? Putting this down. What about what I'm given? Am I given anything? Am I given a derivative?
Yes.
What am I given? 20 feet squared per second. That's the rate that what's changing? The surface area, right? Says it. If the surface area of the sphere is increasing at a constant rate, so I'm given d, what's changing? A dt is 20 square feet per second, right? Do y'all see this is already like a little more complicated than what we've had before? Yes? This is what I want and when I want it, and this is what I'm given. My instant picture is a sphere, and the only thing I really know about this sphere right now is that the volume of it at the instant time is 36 pi cubic feet, right? I know that, right? I know that at the instant. But in general, you know, everything's growing, right? This sphere is getting bigger because it says surface area is increasing, so it's getting bigger. So I don't really have any more to put into that picture. At this point, I might add to it in a minute, but all I know is that, you know, it's growing. You don't need to put this here, but just remember, right? This whole thing is just expanding out like a balloon, getting bigger and bigger and bigger. Okay, so maybe now I need to try and connect the variables. Maybe I can find an equation. Is there any way that we can connect the area of a sphere, not a circle, to the volume of a sphere? So I don't expect that you would know these formulas right off the top of your head. However, on our formula sheets for this class that you're allowed to have on the exam, at the very top of the first page, reference page 1, not very top, top right, you see it has some things there? Do Do you see that it has, for the sphere, what the volume is and what the area is? Let's jot those down over here on the side. For a sphere, so I'm not working over here right now. This is really just me preparing that to get, whatever I need over there, I'm preparing for that. So I know that the volume of a sphere is 4/3 pi r cubed, right? And then the area is 4 pi r squared. Surface area, right? We have a problem. We need an equation that connects V to A, right? Right now, the only thing we have is an equation that connects V to R, right? And A to R. And that's a problem because if we let's say we differentiate this with respect to time, we'll get a dv dt, won't we? We will get a dv dt, and that I'm actually happy to see, right? But what else will I get? A dr dt. And do you know anything about dr dt here? Nothing, right? So you're going to be in a bad situation there. Does that make sense? Because you're going to have dr dt, but you know nothing about it. On this equation, if I take the derivative of this, I'll have dA dt, which is actually good because I have dA dt here, but I'll also have dr dt there as well, right? Which I don't know anything about. So the problem with this problem is that we don't have an equation that connects these two together directly, right? They're indirectly related, but they're not directly related. Make sense? So what I'm going to do is I'm going to take these and I'm going to make an equation out of them. That's what I'm going to do. So the way I'm going to do this, I think the easiest thing for me to do would be this. I'm going to take this equation and solve it for R, and take that answer and put it right here. All right? So if I solve for R here, I would have to divide both sides by 4 pi. And then I'd have to take the square root, wouldn't I? So the square root of A over 4 pi equals R. Now, I'm technically supposed to do plus or minus when I took the square root, but I'm talking about the radius of a sphere. So I'm only going to have a positive radius. Do you all agree that this is what R is? Now I can take that expression and replace that right there. So now this volume becomes 4/3 pi, whatever the radius is, cubed. But the radius is this. So square root of A over 4 pi. Now you may not like it, but is that an equation connecting V and A together? Yes. So if you can differentiate this, it's a big if, right? If you can, you'll have a dv dt in there, and you'll have a dA dt in here. And the only other thing you need, well, you might need to know the volume, which we do, and you might need to know the area. But I think we can get the area. If we know the volume, right? If I know the volume, can't I figure out what the radius of this is? Right? And if I know the radius, can't I find the area? So I should be able to figure out what V and A are if I need, well, I know what V is, but I should be able to find out what A is if I need it. Y'all good?
Could we also solve for R?
You could have solved for R here, yes.
On the V side?
Yep.
This is preference.
I just preferred to take a square root rather than taking a cube root over here, but you could do it either way. I actually have never done it that way. I've always solved this one for R, but it'd be interesting to do that one for R. Okay, this looks horrible, but it's actually not as bad as it looks if we just take a little bit of time algebraically with it, okay? So can I erase this? Yeah? All right, here's what I'm going to do. See if you can follow this. This is V equals, I'm not doing any derivatives yet, I'm just cleaning this up. 4/3 pi, okay, square root of something to the third power really means, well, the square root really means what power? The half. So this is like raising it to the half and then cubing it, right? So you multiply these two powers, and that gives you 3 halves, 3/2. So I really have right there a over 4 pi all to the 3 halves, right? You okay with this? And then, because this is a fraction, I can do the power on the top and the bottom separately. So I can go v equals 4/3 pi times a to the 3 halves over 4 pi to the 3 halves. Y'all still good? This is just a number, isn't it? That's just a number? Okay. So, yeah, I guess I'll go here.
So that's the equation?
This is the equation. All I'm doing is cleaning it up right now, algebraically. I need to differentiate this, right? If I had to take derivative of this, this would be a mess. So what I'm doing is I'm trying to get anything that's a constant out front, and that way I can have the thing I need to take derivative of just by itself. All right? So I have v equals, watch this, this is going to be cool. I'm going to take this 4 pi and put it on top. On the bottom, I'm going to have this 3, and I'm going to have this 3, and then I have a 4 pi to the 3 halves. And then what's over here next to all of that? If I move this under here, what's over here? A to the 3 halves. Right. This is all just a constant, isn't it? It's all just a number. Does anyone see what I can do with that 4 pi? This is the same as 4 pi to the first power, isn't it? What's 4 pi to the first power over 4 pi to the 3 halves power? What would you do to those exponents? Subtract. So what's 1 minus 3 halves? Negative a half, right? Negative a half. So those two together is really 4 pi to the negative half. Y'all buy that? That's what these two are? No?
I thought it was just like not minus, but I thought one just canceled out and it would be 1/2.
Down here?
Yeah.
That would work as well. Yes, you could do that as well. I'm going to get this answer, and then because it's a negative exponent, I'm going to drop it down to the bottom. So this will become volume equals, this is gone, this is gone. What I get on top is a 1. I still have this 3. And then this right here that was on top, I'm dropping it down, and it's now the square root of 4 pi. Because that's what this means, right? Drop this down. This is really 1 over 4 pi to the half, but then you just make that back to a square root. And then I have times a to the 3 halves. I like that. I kind of threw you right into the fire here. That equation's not an easy equation to get. Who has questions? That's our equation though, right? I mean, that is an equation connecting a and v together. So I'm going to put it here. V equals 1 over 3 square roots of 4 pi times a to the 3 over 2. Now I'd like to differentiate that with respect to time. So what's the derivative of the left side? dv dt. Good. Equals, this is all just a constant, right? Just comes for the ride. So I'm going to put it here. 1 over 3 square roots of 4 pi. Okay, times. Now take the derivative of this. Chain rule. So what first? 3 halves comes out, right? The power comes out, 3 halves. So this 3 halves comes out, 3 over 2. A to what power? Subtract 1 from that, you get a half up there. Chain rule. Times, now the derivative of a. Derivative of a? dA dt. Come on, you have a question? Come on. You all following? I know some of you are, but a lot of you are not responsive. There it is. Yes?
Time problem again.
Yeah.
Kind of, the part that confused me was trying to like find like the equation for like what was given and what I want just by looking at the equation. So like usually, how do I word this? Like what's kind of like the methodology to like kind of quickly find out what's given and what's won by looking at like keywords in Word problem.
Okay, so if the surface area, so if I'm looking at this surface area, right? If it's increasing, so I see increasing, I'm already thinking derivative. They're giving me a derivative here. It's increasing at a certain rate, right? This right here has got to be a derivative. It's the rate of change of the area, right? So that's dA dt. They're saying how fast is the volume increasing? That's the derivative of the volume. That's dV dt, right? So how fast? Speed, derivative. Speed of what? Volume. Derivative of volume. Make sense? When, okay, so when are we talking about? At the moment the volume is that. So that's our instant in time, when the volume is this. I don't know if that's,
Yeah.
you're just going to have to do problems to start to make these connections.
Help me out.
Okay.
Are we gonna take the derivative
Of the 1 over 3?
of the 1 over 3 is 4.5?
No, it's a constant. This is all just a number, right?
Oh,
Right, we don't have to do any derivative here. This is just a constant, so it just comes for the ride. Thank gosh, right? Thank God, gosh, whatever you want to think, right? It's a good thing that that's a,
But you have to take the derivative of both of them, correct? Which we did, but it has multiplication, so why don't we do the product?
no, because think about this. When we had go back to before all this shit happened, okay? If I take derivative of 4x squared, right? You don't really do anything with the 4, you just bring it, right? And you just say, what's derivative of x squared? You say 2x, and then you hit it with the 4 and it becomes 8x.
Gotcha.
You did that before, right? And you never touched the 4, you just brought it for the ride?
Right.
Same idea. This is like a 4x squared. And so you're just bringing the 4 and then doing your x squared stuff here.
Gotcha.
Except we've got now a fraction, and then we've got the chain rule. So we're going to have something else on the outside.
Makes sense.
Yeah? It actually turns out, though, and don't ever do this, that if you wanted to treat this like a product rule, you could. Because what does the product rule say? You do derivative of this one times that plus derivative of this times this, right? So derivative of 4 is 0 times x squared plus the derivative of x squared, 2x, times the first one, 4. And you wind up with 8x. So even if you did product rule here, you get it right, but I would,
Some more work, yeah. Makes sense.
yeah, it's way more work. And that would be like, at this point, it'd be like, I'm not sure. Yeah, let's just keep going. All right, so we're here, right? dV dt.